Dissolution of gases in liquids is an equilibrium process. At equilibrium, the rate at which the gaseous solute molecules escape the solution equals the rate at which the molecules re-enter the solution. An increase in pressure results in more molecules of the gas striking the surface of the liquid and entering the solution in a given time. Therefore, at high pressure, more gas dissolves in a given volume of liquid than at lower pressures. This proportionality of the solubility of a gas to pressure was first proposed in 1800 by William Henry and is known as Henry's law. The law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas. Dalton, a contemporary of Henry during the same period, concluded independently that the solubility of a gas is a function of its partial pressure. If the solubility of a gas is expressed in terms of the mole fraction, then the statement of Henry's law becomes: the mole fraction of a gas in a solution is proportional to the partial pressure of the gas over the solution. However, the most commonly used version of Henry's law is: the partial pressure of a gas in vapor phase, P, is proportional to the mole fraction of the gas, X, in a solution. Mathematically, it can be represented as P is proportional to X, or P is equal to KHX, where KH is the Henry's law constant. Further, if you plot a graph between P, the partial pressure of a gas in vapor phase, and X, the mole fraction of the gas in a solution, then you will get a straight line passing through the origin with its slope equal to KH. The graph also shows that as P increases, X, the mole fraction of the gas in a solution, also increases. The Henry's law constant, KH, for some common gases in water as the solvent are given in the table here. On comparing the values of Henry's constant for oxygen and nitrogen, we can infer that the value of KH increases with an increase in temperature. As a consequence, the solubility of gases generally decreases with an increase in temperature. Also, if the dissolution of gases in liquids is considered as a process similar to condensation, then it is an exothermic process, where a dynamic equilibrium is established between the gas and the solution phase. On applying Le Chatelier's principle to this equilibrium, we see that the solubility of a gas decreases with an increase in temperature. It is seen that when water is heated, bubbles of gas appear on the sides of the container well below its boiling point. These are bubbles of air, which are evolved when water, which is air saturated at lower temperatures, is heated. It is interesting to note that hot water tastes flat because the oxygen in it has been expelled by heating. Have you ever wondered why aquatic species are more comfortable in cold water rather than in warm water? This is because the solubility of oxygen is more at low temperatures. Let us now discuss some important applications of Henry's law in the industry as well as in biological solutions. Carbonated drinks are packed under high pressure of carbon dioxide, some of which gets dissolved in the beverage. When the bottle is opened, the partial pressure of carbon dioxide above the solution drops. As a result, some of the dissolved carbon dioxide comes out of the solution as bubbles. Henry's law has an important application for scuba divers. The pressure is very high deep in the sea. As a result, the amount of nitrogen dissolved in the blood and other tissues of deep sea divers increases. If the diver returns to the surface too rapidly, then the nitrogen forms bubbles in the blood as it becomes less soluble due to a decrease in the pressure. These bubbles are dangerous as they can plug small arteries and cause serious damage by stopping the flow of blood to a particular organ. Divers may experience this potentially painful and lethal condition called the bends if they do not ascend to the surface slowly, allowing themselves time to adjust to the lower pressure at the surface. To alleviate this problem, artificial breathing mixtures consisting of 32.1% oxygen, 56.2% nitrogen, and 11.7% helium are used. Helium is 5 times less soluble in blood than nitrogen. As a result, there is less dissolved gas to form bubbles. On the other hand, at high altitudes, the atmospheric pressure is low and there will be less concentration of dissolved oxygen in blood and tissues. Therefore, mountaineers at very high altitudes suffer from anoxia, which is low oxygen supply in the tissues, accompanied by weakness and inability to think clearly. That is why mountaineers carry oxygen cylinders at high altitudes. Let us now discuss the vapor pressure of binary solutions. We shall discuss the vapor pressure of liquids in liquids and solids in liquids. First, we will discuss a binary solution of two volatile liquids, 1 and 2, that are completely miscible in all proportions. In 1886, through experimental studies, a French chemist M. Raoult established a quantitative relationship between the mole fraction of a given component and the partial pressure exerted by it. The law states that the partial vapor pressure of each component in the solution is directly proportional to the mole fraction of it in the solution. Now, if P1 and P2 are the partial pressures exerted by the components 1 and 2 at a certain temperature, then, according to Raoult's law, P1 is proportional to x1, or P1 is equal to P1 naught x1, where P1 naught is the constant of proportionality and represents the vapor pressure of pure component 1 at the same temperature. Similarly, for the component 2, P2 is equal to P2 naught x2, where P2 naught represents the vapor pressure of the pure component 2. Now, if you apply the Dalton's law of partial pressure, the total vapor pressure of the mixture would be equal to the sum of the individual partial pressures of the component 1 and 2. That is, P total is equal to P1 plus P2, or P total is equal to x1 P1 naught plus x2 P2 naught. Let this be equation number 1. Further, you know that for a binary solution, the sum of mole fractions x1 and x2 is equal to 1. Or we can write x1 equal to 1 minus x2. Now substituting for x1 in the equation 1, we get P total is equal to 1 minus x2 P1 naught plus x2 P2 naught. Let this be the equation 2. In the equation thus obtained, we can see that P total is a linear function of mole fraction x2 as P1 naught and P2 naught are constant at a particular temperature. If a graph is plotted for the partial vapor pressure of the first component against the mole fraction, corresponding to the equation P1 is equal to x1 P1 naught, then a plot as shown here is obtained. As you can see in the graph, when the mole fraction of first component becomes 1, the partial pressure of component 1 is the vapor pressure of the pure component 1. Similarly, a plot for the component 2 corresponding to the equation P2 equal to x2 P2 naught on the same set of axes is represented as shown here. Now, as can be seen from the curve, the vapor pressure of the pure component 2 is higher than that of the pure component 1. This means that the component 2 is more volatile than component 1. Now the total vapor pressure of the binary mixture P total is given by the sum of the partial pressures P1 and P2. As you can see in the diagram, the solid straight line gives the plot of P total versus mole fraction. Further, as the vapor phase is in equilibrium with the solution phase, the composition in the vapor phase can be determined by the partial pressures of the components by the equation P1 is equal to Y1 P total and P2 is equal to Y2 P total, where Y1 and Y2 are the mole fractions of the components 1 and 2 respectively in the vapor phase. It is important to note that the above holds true only if the two components in the binary solution are volatile and are completely miscible with each other. Now, if one of the components in the binary solutions is considered to be highly volatile, such that it exists as a gas, then, as you know, its solubility is given by the Henry's law, P is equal to KHX. As can be seen from the equation, the partial pressure P of the highly volatile component or gas is directly proportional to the mole fraction X, and KH is the constant of proportionality which can be equated to P naught. In other words, we can say that Raoult's law is a special case of Henry's law.